Okay, welcome back. This is 9.5, alternating series. And to this point, the series we've been working with have all had positive terms, and we're going to develop some tests to deal with series that may have some negative terms. The first kind of type is where we have negative, then positive, then negative, then positive, things being added together. So we have two basic forms. Sorry, these are the same thing, but obviously, in one, you'll have an exponent of n plus 1, on the other one, on the negative one, you just have an exponent of n. So this guy will have, if you put in n as 1, you'll get a positive. So the odd terms will be positive. And for this guy, the even terms will be positive. So again, it's a sum of an infinite number of items that are alternating in sign. Okay, so an example, maybe an example's in order, something like 1 minus 1/2 plus 1/4 minus 1/8 plus 1/16 minus ... And we could write that as a sum going from n equals, I guess we could start at 1 to infinity, of 1 all over 2 to the, I guess, n minus 1. And this would be the a sub n part. So to deal, when we go to test these things, we're going to be separating out this negative 1 to whatever power. So in this case, because the odds are positive, it'll be negative 1 to the n plus 1. I got to smush that in, I'm sorry. So I rewrite that. The sum negative 1 to the n plus 1 of n equals 1 to infinity, where our a sub n part is 1 all over 2 to the n minus 1. Okay. Okay, so that's what they look like. The test we'll be using when you see one of these forms is the alternating series test. And the test is done on the a sub n portion. We kind of just forget about the negative 1 part in these items, and we just do the diagnostic on the a sub n. Okay. The deal will be you have some positive a sub n expression, and you're trying to see if your series, of either type, I'll just put the n plus 1 type here, then this thing is convergent if you have the following criteria holding. So first, what is it? It's my stupid notes are screwed up. The limit of a sub n as n goes to infinity, this thing has to go to 0. And then the second criteria is that the terms, the a sub n terms, are decreasing. Okay, so you have to prove that a sub n is less than or equal to a sub n plus 1. To prove these, we use the monotonicity test that I showed you in 9.1 in the previous lecture. So prove using tests for monotonicity. Okay. Right. So the reason why it works is not intuitive, really. The proof is kind of a bit more involved than I would want to do, but I'll walk you through it just for the sake of the video. So the proof of this fact, it sort of relies on some other facts that you need to have kind of encoded in your brain. Usually we don't encode these facts very well. the first fact we need to recall is that things that are monotonic and bounded, monotonic plus bounded, in those cases, those things are convergent. Okay, this was a theorem, convergent. This is a theorem from 9.1. Okay? If it's increasing and it's bounded above, it'll converge. If it's decreasing and bounded below, it'll converge. Okay? So in this case, we'll have basically a sequence of partial sums that'll be increasing, and it's also bounded above. Okay? So it'll end up being convergent. There's one other fact, though, that we kind of would need, and this, I said it in one direction. I said if the even terms of the sequence and the odd terms of the sequence go to the same place, the series is convergent. No, the way we used it was disproving convergence. So we would say if the odd terms and the even terms have different limits, then the series is divergent. So I guess we kind of use the contrapositive, right? So if the series is convergent, and again, when we talk about convergence of the series, we're really talking about the convergence of the sequence of partial sums. Okay? So we can analyze these series as sequences of, for S sub 1 is the first term, and S sub 2 is the first term plus the second term, S sub 3 first term plus the second term plus the third term, etc. That becomes a sequence, and then we say this sum converges if that sequence of partial sums converges. Okay? So when we talk about this thing being convergent, we're talking about a sequence converging. Yeah, that's still kind of the issue. But in particular, if a sequence is convergent, so let me just replace this thing rather with this S sub n sequence. If this S sub n sequence is convergent, then the sequence of the odd terms, which we can write 2n plus 1 or 2n minus 1, I think I wrote it in my notes as 2n minus 1. This sequence and the sequence of even terms will have the same limit. Well, I guess you could say that pretty much for any sequence that is convergent. Can you say that for any sequence that is convergent? And I don't think you can, right? If a sequence is convergent, yeah, I think you can. If a sequence is convergent, then any subsequence it has to be convergent to that particular limit. I think the proof, though, uses it the other way around. If the sequence of even terms and the sequence of odd terms have the same limit, that implies it's convergent. So it's more like if this holds, then this holds. So I'm really using it in that direction. Okay, so whether or not, regardless of that being true, and one of the problems with later on in advanced calculus when you're trying to prove limits for functions, you're thinking of how do I prove that using limits of sequences. You have an infinite number of sequences to prove, that something is convergent by proving that every possible subsequence converges. It's just an overwhelming task. You can't do it, So that becomes difficult, and that's kind of I don't know, the hard part of it is if you're playing the clarinet. There's there's this crossover place. So if you play the cello, it's as you're going from fourth position up in the thumb position, it's that crossover point right there that's really difficult, and it exists in math. At least for me, it did. But anyways, long story short, yeah, if if the even term, if the limit of the sequence of even terms equals the limit of the sequence of odd terms, then the sequence itself is convergent. So if, let me write that then. If, so long story short, if the limit of s sub 2n is equal to the limit of s sub 2n minus 1, then you could say the limit of s sub n is convergent, and it equals this limit here. So whatever this thing was, if it was L, then this thing will also equal L. Okay. And you can prove it using epsilon delta proof. Essentially, any number is either an even or an odd term. So as you look further down the sequence, you could kind of say there's going to be an epsilon such that this thing will always be within L, and this thing will always be L, and then any number is either this form or this form. So therefore, you can find a number far enough based off of these two limit definitions such that if you push this guy beyond it, it'll be convergent to that L as well. So, it's a lot. It's a lot to take in, but that's kind of the idea. So anyways, long story short, yeah, we need these two kind of facts. We need the fact that monotonic and bounded equals convergent. We also need the fact that if the limit of the odds and the limit of the evens equal the same thing, then the limit of the sequence itself is convergent and it equals some number L. Okay. So finally then, that's kind of the prerequisite information that's probably missing from the book and from my lectures and from your education. Let's get into the proof now. So what's our supposition? We suppose we have this sequence A sub n it's a series such that the limit of the terms of the series is equal to 0, and the terms of the series are decreasing. A sub n plus 1 will be greater than or equal to A sub n eventually. Okay, it's always about eventually for us. So I can write eventually, I guess. Okay, so having those suppositions, we consider then this sequence of partial sums for S sub 2n. Okay, so S sub 2 is going to be A sub 1 minus A sub 2. S sub 4 is going to be A sub 1 minus A sub 2 plus A sub 3 minus A sub 4. Right? So in particular, in this proof, I'm considering the version, and I guess I missed my negative thing here. I'm considering the version where the odd terms are actually positive. But I could probably pull off this proof in the opposite, for the opposite case as well. It's just we don't have, I guess we don't have time. I could do it, I just don't feel like it, I guess. But anyways, you go on and on with this, and you get an expression S sub 2n, which will be A sub 1 minus A sub 2 plus A sub 3 minus A sub 4 plus dot 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 plus all the way at the end here we have A sub what is this, 2n minus 1 minus A sub 2n, right? So the proof kind of hinges on our ability to rewrite these finite sums as in curious ways. So the first rewrite of S sub 2n allows us to see that this thing is what do we want to say it is? It's an increasing sequence, okay? Because eventually, if we could show that it's increasing and bounded, it'll be convergent. So to show it's increasing, what you can kind of do is group the terms together. So you can group these two terms together, group these two terms together, etc. And because it's, the supposition that a sub n plus 1 is greater than or equal to a sub n, well, that just worked against me, didn't it? All right. Yeah, sorry, it's decreasing. This would indicate it's increasing. Sorry, I screwed that up. So this is less than or equal to, crud, sorry. A sub n plus 1 is less than, and now if you have this inequality, so it's decreasing terms. Here in my sum, all of these will be positive because a sub 1 will be greater than a sub 2. So what you have as you go from term to term will be an increasing sequence. So if you looked at s sub 2n plus 2, what is that? Well, it's just s sub 2n, and then you're adding something onto it. In particular, a sub 2n plus 1 minus a sub 2n plus 2. Okay, so going from here to here, it's definitely an increasing sequence. Okay, so that's one part of the monotonic plus bounded part that we're trying to prove. The other part comes from rearranging these terms. So I have my s sub 2n. If I rearrange them like this now, a sub 1 minus a sub 2 minus a sub 3 minus a sub 4 minus a sub 5 minus dot dot dot, and then these last terms, what are these going to be? It's going to be a sub 2n minus 2 minus a sub 2n minus 1, and then minus a sub 2n. This thing is a sub 1 minus a whole bunch of junk, right? So inside here, because of our decreasing statement, a sub 3 is less than a sub 2. So this is a positive thing, and we're subtracting it away. All of these are positive things, and we're subtracting them away from a sub 1. So what this tells me, this part tells me, is that our sequence s sub 2n is bounded above by a sub 1, okay? Because we're always taking stuff away from a sub 1 to get to our next term. Right, so I've shown then that it's monotonic and it's bounded, and that implies it's convergent. Okay, so hence I note the sequence s sub 2n, the sequence of partial sums, is what did we say? It was increasing and bounded above. So it's convergent. Okay, great. I need to show that s sub n in particular is convergent, which is different than s sub 2n. S sub 2n is a sequence where I'm adding on 2 extra parts every time I go from one to the next. So that's not exactly the same as s sub n. The workaround comes from proving this. Okay? So if I could show that the even terms and the odd terms have the same limit, then I'll have that s sub n is convergent, and then the series converges because the sequence of partial sums converge. Okay. So, right, so I need to show that s sub 2n minus 1 is convergent. So I take a look at s sub 2n. So consider s sub 2n, in particular, minus 1. Okay? So s sub 2n minus 1 is going to be a sub 1 minus a sub 2 plus a sub 3 minus a sub 4 plus dot 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 plus, and then the last one is a sub 2n minus 1. Okay. So we want to compare that with s sub 2n. Okay, here's s sub 2n minus 1 right here, and then here's s sub 2n. So what's the difference between these two? The difference is this guy, right? We can make an equation. We can say s sub 2n minus 1, and then to make this equal this, what do I have to do? I have to basically add a sub 2n onto both sides of the equation, if you wish. I mean, literally right now, if I just subtracted a sub 2n on it, it would equal s sub 2n. But I want to write it in the other way around. I want to write it, yeah. I want to use the fact that I know the convergence of the. Sorry, I lost you. Yeah. So hopefully you see s sub 2n minus a sub 2n. So if I just tack on a minus a sub 2n right here, this will equal this. This and this will be the same. So s sub 2n minus a sub 2n is equal to s sub 2n. I can add a sub 2n to both sides. And then I can consider this expression and take the limit of it. Okay, so note then the limit of s sub 2n plus a sub 2n as n goes to infinity. Well, I know this s sub 2n thing is converging to something. I could call it L, whatever I want. Then the limit of a sub 2n, the nth term of the 2nth term of the terms of the series, well, I know something about that from my supposition. That was one of my suppositions. I suppose that these a sub n things go to 0. A sub 2n is just an a sub n. It's just farther out, right? So if this thing's going to 0, then certainly this thing will go to 0. Okay? So the limit of this thing will be 0, and you just get L. And if you consider then taking the limit of both sides of this thing, what do you get? Well, that should equal the limit of s sub 2n minus 1. In other words, the limit of s sub 2n is equal to the limit of s sub 2n minus 1, which then implies from the second sort of thing that somehow you magically know about is going to happen, right? So this implies the limit of s sub n is equal to L, and that in turn implies the series -1 to the n plus 1 of a sub n from n equals 1 to infinity is convergent. Okay. So the deal is when you're handling proofs like this, you kind of want to skim it and look for things that maybe you don't know about. In particular, probably in the book, this would have been embedded in the exercises, like problem 95 or something, which I probably didn't assign because I assume you don't know how to do epsilon delta proofs like a madman, So it was probably in the book, and then you go and read the theorems, and it's based off of some needle in a haystack from your homework assignments. But at least this one, though, we should be kind of familiar with monotonicity and bounded equals convergence. That theorem is kind of used over and over in the proofs. So I don't know. Yeah, it takes a while to master these things. But anyways, long story short, we have another test then for dealing with these sequences. So let's look at problem 6. We have the series n equals 1 to infinity of -1 to the n plus 1 times n all over 3n plus 2. So I recommend when you're working with these guys, you want to kind of pick out the a sub n part. Okay, so n equals 1 to infinity of -1 to the n plus 1 times n all over 3n plus 2. Okay, so this is my a sub n. That's what I'm doing my diagnostic test on, right? I talked about series in class being like animals. What we're doing is cutting open the animal and taking out its guts, right? I don't need this part of it. I don't need the spine or whatever it is. I just need the intestines, okay? So that's what I'm doing my test on. It's a two-step test. So first you want to take the limit of a sub n. you have to show that that goes to 0. If it doesn't, you got trouble, right? So in this case, it does not, obviously. The limit is just n over 3n, which is 1 over 3. Okay, so that's not equal to 0. You can't technically say it doesn't converge because that's really the nth term test you need to take into consideration. By the nth term test, because if you read the book, the test doesn't say, well, if this doesn't work, then you can say it's divergent. And you really want to follow the rules because there's all these weird technicalities and there's tons of series you can't even imagine. So you kind of want to not invent your own rules. You want to follow the way the thing is written. Being good at following rules will help you here. Sometimes that can hamper your creativity, though, right? But anyways, by the nth term test, we know that the limit of this other expression, -1 to the n plus 1 times n all over 3n plus 2, that's going to be, that does not exist because the even terms will go to -1/3 and the odd terms go to +1/3. It's diverging by what the book is calling oscillation. Okay, so this does not exist. The nth term test says if that does not equal 0, then it's divergent, hence divergent. So it's, I mean, I'll let you get away with it. If you found this limit was 1/3, I'd probably let you get away. Well, I'd be ticked, and I'd be ticked because it would take me a while to explain to you why it's wrong. But you would need to do some extra work to really show that that's true. Okay, you would need to convince me beyond a shadow of a doubt, and you know. Okay, but okay, so there's that. It's not really all that complicated. And apparently, I only have one freaking example of this. We'll probably be seeing more later. Anyways, the alternating series remainder theorem. So if it's convergent, I don't have a nice formula like I did with the geometric series to say it adds up to 3 or it adds up to 5. Okay, what I'm going to have to do is an approximation using terms of the series. I talked about this in class. It turns out that we can just use the first couple of terms. We don't need to know the whole thing. Okay, so it's theorem. This is the alternating series remainder theorem. And the idea is kind of neat to see visually. So if you start here at 0, I guess, and then you add in a sub 1. Okay, so I'm over here at a sub 1, which is really equal to s sub 1, right? The first partial sum. Okay, so I journey over here on the number line, and then I subtract away a sub 2, so I'm going to be going this way on the number line, and that will be s sub 2. And then I add in a sub 3, and that'll give me s sub 3. And then you just keep going on this process over and over and over until you're kind of down here. This would be something like s sub 2n, and then this guy would be something like s sub 2n plus 1. Okay. The actual limit of the sequence would be in here somewhere in between these two guys. And then the difference between these two guys, right, is kind of what we're after. And I don't even have to use s sub 2n. I can just say s sub n and then s sub n plus 1, right? So what is s sub n, right? S sub n is equal to a sub 1 minus a sub 2 plus a sub 3 minus a sub 4 plus dot 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 plus a sub n minus 1. And let's say this is n minus 1. So I'll look at s sub n minus 1 first. And then if we add in a sub n, we'll get over to s sub n, right? So s sub n minus 1 is this, and then s sub n is just the same thing. but adding in a sub n. Okay, so what? Well, the difference between these two terms, s sub n and s sub n minus 1, is less than or equal to a sub n, right here. And then because the limit is in between them, you can go further and say that the actual sum, presuming it is convergent, you can say the actual sum then, s minus the nth partial sum has a distance less than that a sub n. Okay? So again, what am I saying? The distance from here to the next term is basically equal to a sub n. So the distance from s sub n minus 1 to, or s sub n on this side, the distance from s sub n to L, this little distance is less than the distance traveled to get to the next term in the sequence of partial sums. Right? So this is the statement we're working with. This is the grand finale of theorem 9.15, which is the alternating series estimation theorem. So supposing that your series converges, or your sequence of partial sums converges, then you're going to have this inequality holding, and you can use it to do estimations. And there's two types of kind of estimations we want to pull off. We want to know how many terms of the series do I need to ensure a certain margin of error. So to ensure that my error is less than 0.001, how many terms do I need to add up? The flip side of that coin is, what was the flip side of that coin? If I have like 10 terms, how good is that approximation? So you're trying to find, given an n value, that margin of error. Okay? So those are the two types of problems. Let's look at number 30. We want to approximate the sum using the first 6 terms. Okay. And this, I have in my notes as it follows example 4, but let's take a look at number 30. We have a series from n equals 1 to infinity of -1 to the n plus 1 times n all over 3 to the n. Okay, so first I have to show it's actually convergent before I can use this theorem. And so first off, I want to show the limit of a sub n, which is this portion right here. So n all over 3 to the n equals 0. Okay, this is infinity over infinity, so I can do L'Hopital's. The derivative of n is 1. The derivative of 3 to the n is 3 to the n ln 3. So certainly that'll go to 0 as n goes to infinity. Secondly, I need to show that that a sub n plus 1 is greater than or equal to, sorry, the other way around, I did it again. I need to show that a sub n plus 1 is less than or equal to a sub n. I need to show it's decreasing. Okay, so if you remember back in 9.1, I gave you 2 types of proofs for doing these algebraically. I gave you the calculus proof. You could take the derivative and show it's negative. The particular algebraic proof I want to use is to show that a sub n plus 1 all over a sub n is less than or equal to 1. Okay, so basically you just divide both sides by a sub n. And if you can prove this expression works, then you're good to go. Okay. So I need to prove that, and in order to do that, I need to make this ratio a sub n plus 1 all over a sub n. So a sub n plus 1, I'm plugging n plus 1 into this expression. So I have n plus 1 all over 3 to the n plus 1. And then that's divided by n all over 3 to the n. I rewrite that as a complex fraction, so I do reciprocal. Simplify that. So I have n plus 1 all over n times 1 all over 3, okay, which will equal n plus 1 all over 3 n's. And you want to compare that to 1. Okay, so how am I going to do that? Well, look, n plus 1 is definitely less than or equal to n plus n when n is greater than or equal to 1, right? What is this side? That's two n's, right? So and on top of them, we could say n plus n is less than or equal to n plus n plus n. Again, when n is greater. So what is this side equal? That equals 3n. Okay, so the transitive property says that n plus 1 must be less than or equal to 3n. So I have something less than something else when n is greater than or equal to 1. So this will definitely be less than 1. So that's a direct proof. When I used to do these, I kind of felt like it was fake. You know, it's like, well, we're just putting the inequality there. That doesn't really prove anything. And honestly, I'm right. You really need to do a direct proof to prove these things, and we don't do that. It's a real crime. It's a crime against mathematics. I guess we just don't have time to teach everybody all this stuff. And, life is finite. You don't want to be 46 still trying to rummage through little details that you need to learn in a week back in your undergraduate program, in your freshman, sophomore year of college. I don't know. Whatever. Here's number 8. Oh, we're not done with that. Good. I was just proving it was convergent. We're supposed to approximate this thing, right? Okay, so sorry about that. So I want to approximate this thing. Let's see if it gives me some sort of estimation I want. No, it just wants me to approximate with using the first 6 terms. So it's convergent, so I can do that. So I need the first 6 terms, and then I need to make a statement about how good the approximation is. So n equals 1 to 6 of -1 to the n plus 1 times n all over 3 to the n. What the frick is that, right? It'd be 1 all over 3 minus 2 all over 3 squared plus 3 all over 3 cubed minus 4 all over 3 to the 4th plus 5 all over 3 to the 5th minus 6 all over 3 to the 6th. Right? Right, so you can add that up. I probably did somewhere in my life. It's equal to 5/27ths, and that should give you a pretty good approximation for this infinite series up here. Okay, so we don't have a formula for it like we did with the geometric. You just have to take it on faith that this thing is a good approximation. How good of an approximation is it? Well, now we can go back to this formula and talk about how good of an approximation it is. So s minus s sub n. And so our n value in this case is the number of terms, the 6, right? So the actual sum minus this approximation here, s sub 6, is less than or equal to a sub, is it n or is it n plus 1? It's actually the next term. Sorry, it should be n plus 1 up here. So a sub 7, okay? And find what a sub 7 is. Well, a sub 7 is just the next term that would have been in line here. So it's just 7 all over 3 to the 7th. And that's 7 all over 2187. Okay. So it's a pretty small number. The difference between these two is not significant. It's a lot less than 1. So that's good. So what else can we say about it? We can actually find a boundary for the actual sum. So I could say, s, if I expand this inequality, s minus s sub 6 must be less than or equal to 7 all over 2187, greater than or equal to negative 7 over 2187. And then you could add s sub 6 to all 3 sides because we know it's 5/27ths. Okay. I'm doing a bit of fancy footwork with my calculator. I found that to be 398 over 2187 less than or equal to s less than or equal to 7 all over 412 all over 2187. And then we can get some approximations. S is in between 0.18198 and 0.1883859. So you say it's about 0.18, right? It's in there somewhere. Okay, great. Let's go back now and take a look at, I guess we have some more examples of convergent and divergent series. And then we'll look at another approximation type. So here's 8. We have the series from n equals 1 to infinity of -1 to the n all over e to the n. Again, the a sub n portion is what interests me. So all I'm doing here is finding whether it converges or not. Okay. So I got -1 times 1 all over e to the n. So first I need to show the limit of this thing is 0. So the limit of 1 all over e to the n, that's obviously 0. It's L over infinity type, so that'll be 0. Secondly, then I want to show the ratio, the terms a sub n plus 1 are decreasing, right? I need this to be less than or equal to a sub n. And in this case, you could do a rate, again, you could kind of prove that a sub n plus 1 over a sub n is less than or equal to 1. So you take a look at that expression, a sub n plus 1 all over a sub n, that's equal to 1 all over e to the n plus 1 all over 1 all over e to the n. And if you multiply that out, you get e to the n all over e to the n plus 1, which is, by rules of exponents, 1 all over e. And e is around 3, so 1/3 is definitely less than 1. So that proves it's strictly decreasing in this case. Okay, so it's definitely convergent by the all-Chang series test. Let's look at number 13. So I have the series -1 to the n all over the square root of n from n equals 1 to infinity. Again, I'm splitting off the a sub n portion, considering that. So I need the limit of 1 all over the square root of n as n goes to infinity. Again, that'll be L over infinity, which is 0. And secondly, I need to show the terms are decreasing. So again, I'm going to do a sub n plus 1 all over a sub n. That's usually my go-to choice for proofs. So in this case, it'll be 1 all over square root of n plus 1 divided by 1 over square root n. That's equal to square root n all over square root n plus 1. And then when n is greater than 1, obviously you have something small over something big, and that's always going to be less than 1 in my book. So it's convergent. Let's look at another one. I like this one because it deals with factorials, and factorials are going to be kind of an issue coming up in life. Number 19. You have the sum from n equals 1 to infinity of -1 to the n all over n factorial. So first I need to show that the limit of the terms is decreasing, or sorry, the limit of the terms is equal to 0. Obviously this is L over something getting huge. And remember, these limits are always going to infinity. Okay, so it's n factorial. It just grows very, very fast. It goes faster than any exponential term. Okay, so k to the n will be not growing as fast as this, but anyways, it'll be 0. Okay. Secondly, then, a sub n plus 1 all over a sub n. This is why I want to look at it, because this kind of cancellation is going to become important here later on. So you remember what n factorial is, I hope. Remember, 3 factorial is just 3 times 2 times 1. N factorial in general is going to be n times n minus 1 times n minus 2, all the way down to 3 times 2 times 1. But sometimes it's better to use a recursive definition of n factorial. N factorial is just n times n minus 1 factorial. Right? Just like 5 factorial is equal to 5 times 4 factorial. 5 times 4 times 3 times 2 times 1. So it's this definition, which I think is a lot easier to work with than always having to write this thing out. So generally I'll say go to that. So a sub n plus 1 is going to be n plus 1 factorial. And then a sub n is going to be n factorial. Or sorry, 1 all over that, right? So it's 1 all over n plus 1 factorial all over 1 all over n factorial. Right? Because a sub n portion is 1 over n factorial. So if I put in n plus 1, I get 1 over n plus 1 factorial. Okay, rewriting it, you get n factorial all over n plus 1 factorial. N factorial is let's just leave n factorial as it is, but n plus 1 factorial, I can pull this trick on, right? So n plus 1 factorial is n plus 1 times n plus 1 minus 1, which is n factorial. In other words, the n factorials cancel, and I'm just left with 1 all over n plus 1. And then when n is greater than or equal to 1, this will be like 1/2, 1/3, 1/4. You always got something small or something big. That's less than 1. Okay, so again, this guy's convergent by the alternating series test. Okay, enough of that. Let's do one more of these approximation game problems. So this, the last one, we kind of were told, okay, let's use the first 6 terms to approximate the series. And then on top of that, how good is the approximation? Here we're told we want a certain approximation. In particular, we want our error, in other words, the difference between s and s sub n to be less than 0.001. And then you have to find n. Okay, so before we were kind of finding the error part, this part. Now we're finding this part. Okay, so how do I do that? 34. I have the series from of -1 to the n plus 1 all over n to the 5th. Let's presume this thing converges. Okay, I'll just take it under assumption. What do we want? We want s minus s sub n to be less than 0.001. We know from our theorem that s minus s sub n will be less than or equal to a sub n plus 1. Okay. A sub n plus 1 is just using this, you know, what is this, times 1. And so I look at a sub n, which is 1 over n to the 5th. A sub n plus 1 is 1 all over n plus 1 to the 5th. So in other words, I need this thing to be less than this thing for life to work out. I need 1 all over n plus 1 to the 5th to be less than 0.001. So there's a couple ways you can do it. You can play around with the inequality and solve for n. Later on, you'll probably be wanting to do trial and error because these expressions won't always be of the form that you'd be able to solve. Because if there's an n factorial in here, you know, how do you do the inverse of a factorial? Right? How do you undo that? It's just not something we do. So you'll probably want to go trial and error. You start out with n equals 1, and you plug 1 into here and see if it's good enough, right? So this would be 1 all over 1 plus 1 is 2 to the 5th. Go to your calculator, it's about 0.03. That's not good enough. Okay. So you try n is 2. And you keep going until you get something less than that. So n is 2 is 1 all over 3 to the 5th, which is 0.004 about. Still not good enough. So you go n is 3. You get 1 all over 4 to the 5th. This time it's 0.00098 about. And that definitely is less than this. Okay, so hence we're going to want our s sub n to be s sub 3. Okay, so hence we want n equals 3, so we need the first 3 terms of this series up here. So I need to put in, you know, what is s sub 3? S sub 3 would be putting in 1, I get a positive, so it'd be 1 all over 1 to the 5th. Then a sub 2 is minus 1 all over 2 to the 5th, and then plus 1 over 3 to the 5th. Right. So basically, you need to go all the way up to the one before this guy. All right. This is a long section, really, because they try to wedge in this other stuff about absolute and conditional convergence. And if my memory serves me correct, the difference between something that's absolute and conditional convergence comes down to being allowed to kind of mix up the terms in the series. If it's absolute convergent, it seems like no matter how you mix it up, it's going to converge. But I'm not sure. I don't remember. So don't take me at word. You can do your own research. Everybody has Google now. I didn't have that back in my day. So anyways, how does this work? I can present you with a flow chart. Okay? So first you're going to ask, is the series of the absolute terms of the series, is the sum of the absolute terms of the series convergent? If so, then it's called absolutely convergent. The original series, A sub n, is absolutely convergent. And that also means that the original series is convergent. Okay? So it's super convergent, I guess. So it's a quick way, if you can kind of look at one of these guys and imagine the absolute value of the terms of sequence, say, oh, that looks familiar, then you can do this test and you'll kind of know your answer. Okay. So if this is convergent, you know, it's like a flow chart, yes, then you go here. If no, then you have to do another kind of inspection. You have to look to see if the original series is convergent using your usual tests. Is the series A sub n convergent? Right? Is the original series convergent? So you use your ratio, your comparison test, your integral test, whatever. If yes, they're going to call that conditional convergence. You know, the original series is conditionally convergent. If no, then it's just divergent. Okay, so finally, you end up at the end, at the bottom, the series diverges. Okay, so when you do these problems, you kind of want to start here and then work your way down the chart. So let's try the versions, the different permutations of this event. We'll start with 39. The series from n equals 1 to infinity of negative 1 to the n all over n factorial. Okay. So step 1, you ask yourself, is the sum of the absolute value of the terms of the series convergent? Okay, so what is this thing? Well, when you take the absolute value of these negative 1 things to the whatever power, the absolute value will just kill them off. Okay, so this series will become n equals 1 to infinity of just plain old 1 over n factorial. Okay. So we have to figure out, is this thing convergent? It's not really, at least in my opinion, easier to see, but we can actually do a direct comparison test. Okay. In particular, 1 over n factorial, it just grows like bananas. In my direct comparison test, I'll compare the guts of this series, the 1 over n factorial, to 1 over 2 to the n, which is basically the guts of a geometric series that's convergent. Okay? So note, the series 1 all over 2 to the n is a geometric. R value is 1/2, such that the absolute value of that is less than 1, so hence it's convergent. Okay. So anyways, like I said, n factorial is huge after a while. It's going to beat up this 2 to the n. This 2 to the n is going to be small compared to that. So you're going to have something small over something huge, and over here something small over something not as big. Okay, so this guy is going to end up being bigger. And then by the direct comparison test, it's kind of like this guy is existing underneath this guy. This guy is convergent, so it'll force this guy to be convergent. Okay, so hence our series 1 over n factorial converges. This series was the absolute value of the original series, and in our flow chart, what does that mean? Well, we started here. Does the series, the absolute value, converge? Yes. So it must converge absolutely. Okay. So the original series converges absolutely. All right, then. Let's look at another. This is 45. This time we have a series n equals 2 to infinity of -1 to the n all over n ln n. Okay. So again, your first step, start with the absolute value of that thing. And the absolute value will kill off that -1 to the n power factor. Okay, so you just have the series 1 over n ln n. Okay, this probably doesn't look very familiar. You can try to do a comparison, but you'll with the harmonic, but you'll be having something that'll be less than the harmonic, and that won't imply convergence, okay, or divergence in this case. But it does look like something I know how to integrate. In particular, 1 over n is the derivative of ln. So I think I would be able to integrate that and do an integral test. I don't suppose this thing is positive, continuous, and decreasing. I can kind of just look at it and know. So you got the integral of 1 all over x ln x dx from 2 to infinity. And you do a u sub for ln x. du is 1 over x dx, so therefore dx is x du. Okay, so this critter will become the integral of 1 all over x times u times x du. Okay, so nice little cancellation there. It turns into a natural log integral. Ln of the absolute value of u, which is the ln of x, ln of x, from 2 to infinity. So I got the ln of the absolute value of the ln of something going to infinity minus the ln of the absolute value of the ln of 2. Okay. So as something goes to infinity and you're putting it inside the ln is going to go to infinity. So you have basically this thing going to infinity. And then again, the ln of something going to infinity is infinity. So this will be infinity minus L, which of course is infinity. In other words, it's divergent. So on the flow chart, where are we? We asked, is this convergent? No. Okay, so now we have to go back and look at the original series. Does that thing converge? So secondly, then, I have to go back and see if this series converges. Okay. And because of that -1 to the n, we know it's an alternating series. So firstly, we look at the limit of 1 all over n ln n, and certainly that goes to 0. It's L over infinity. Secondly, then, we could probably do some sort of a sub n plus 1 all over a sub n test. if you don't like that, you can do apply a derivative would get the job done. I'm a little wary about that, so I'm gonna try this and see what happens. 1 all over n plus 1 times ln of n plus 1 all over 1 all over n ln n. Okay, so that will end up being n ln n all over n plus 1 ln of n plus 1. Okay, and then I'm comparing that to 1. Okay, the natural log of n is an increasing function. Okay, so just this on its own is going to be something small over something bigger. On the other hand, this part right here is also that same characteristic, something small over something bigger. Okay? Likewise, the something small is going to be greater than 1. So when I multiply these things together, there's not the possibility of small times small becoming somehow bigger. Or small, yeah, it's well, yeah, it has to be bigger. What I don't want to say is small times small coming smaller, because then maybe there would be a fight here or something. Small times small here is going to be smaller than this times this. This is bigger times bigger, which will end up being bigger. There's no possibility that this times this is going to make this entire expression smaller than this entire expression, because everything is greater than 1. It's kind of like if a is greater than 1 and b is greater than 1, then a times b will be greater than 1. You pretty much have to go back to your axioms for inequalities, I think, to really make a good go of that proof. And it'd be another direct proof, and I'm just not that great with the inequalities, I have to admit it. So anyways, eventually the numerator is going to be less than the denominator, just because the numerator will always be less than the denominator. Maybe I could say something like ln of n is always less than ln of n plus 1. Okay, that's definitely true. You can multiply both sides by n so long as n is increasing, I think. So you say n ln n is less than n times ln of n plus 1. And then this thing would be less than n plus 1 times ln of n plus 1 somehow. I won't bore you with the details, but struggling. Anyways, let's look at, are we done with that one? No, we just showed it was divergent. Or no, we showed this thing was convergent by the all-chaining series test. So if it goes to 0 and the terms are decreasing, it definitely converges. So where are we on the flow chart then? On the flow chart, we know that this series does not converge, so we went to here. Then we found that this series does converge, so we went to here. So the original series is conditionally convergent, long story short. The series -1 to the n all over n ln n is conditionally convergent. All right, let's see what else we got. There's going to be one that's divergent, totally divergent. Let's look at that one. And that'll be our last one. So sorry, it's a long section. I wanted to do those proofs. Hopefully you just freaking fast forward over the proofs. I'm just doing them for my own practice to a certain extent. Some proofs are very important to me for some reason. Sum n equals 1 to infinity of -1 to the n plus 1 of n squared all over n plus 1 squared. Okay. So again, first start by considering the sum of the absolute value of the terms of the series. And again, in this case, if you take the absolute value, it's going to just clear out that -1 to the n plus 1. So in this case, we're considering the series n squared all over n plus 1 squared from n equals 1 to infinity. I'm thinking about the limit of this thing. I can quickly take that limit, right? And so by the nth term test, I'll have a conclusion. So the limit, so n squared all over n plus 1 squared is equal to the limit of n all over n squared, which is just the limit of 1. So that will equal 1, which does not equal 0. So by nth term test for divergence, the series diverges. Okay? So in the flow chart, we know it's not absolutely convergent, and we continue down. So secondly, we're going to have to consider this guy by itself, and it looks like an alternating series, so I have to do an alternating series test on it. Okay, so the series A sub n is alternating. So do your alternating series test. So step 1, we have the limit of the terms of this series, and then again, just from above, we see that this thing won't work. So what it really will come down to then is considering the nth term test for divergence. So consider then the limit of the terms of the series, this limit of -1 to the n plus 1 times n squared all over n plus 1 squared. The even terms, because of this negative here, the even terms will always be negative, and it'll go to -1. The odd terms, because of this thing, the odd terms will always be positive, and it will go to +1. Okay, the fact that you have even terms going one way, odd terms going the other, imply that this limit does not exist. Okay, and that's certainly then not equal to 0. So finally, you can conclude by the nth term test, the thing is divergent. Okay, so it's not conditionally convergent. It's not absolutely convergent. It's just plain old divergent. Okay, great. We'll see you later.